Good afternoon, honorable judges and professors, and we're the team from Puching Middle School. And our team members are Ngai Chi K, Tam Chi Hang, and me, Joshua Chung. And our topic is from closed match problem to generation of identities of binomial coefficients and trigonometric terms. So our presentation will be divided by four sections, and this is the first section, the introduction. So now, our original problem is coming from a primary mathematics competitions in Australia, and which is consists with two teams playing a hockey game. So we are finding the number of ways the first 12 goals being scored, such that the game is relatively close, where relatively close is defined as the absolute difference of the goal between the two teams is always less than or equal to 2. So we can restate the problem mathematically to an object located at the origin of a Cartesian plane, and for each step we may move it upwards or rightwards by 1 unit. So we need to find the possible outcomes of the first 12 steps are there, such that the absolute difference of the coordinates of the object has never exceeded 2. So here's a simple illustration. As we can see, the coordinates 3, 6 violates the rule that the absolute coordinates difference must be less than or equal to 2. So it's not a relatively close match. So now we have some simple definitions, where x, y being the number of goals of the two teams at a certain instant, and n be the number of total goals, which is n equal to x plus y, and d be the maximum goal difference of the two teams. So now, our original problem, d is equal to 2. So we also define c be number of possible ways to achieve a certain state temporarily, where the value of c at a certain state is determined by the sum of its predecessors. So from those facts, we can construct a counting tree with 13 rows, labeling each node by x, y, and z as shown here. So from this tree, it's quite obvious to find the answer, which is 972. So now we'll generalize the problem. What if d and n are just arbitrary non-negative integers? So now we have to find an explicit formula depending on d and n to find the number of different ways. So now we move on to the second part, which is the combinatorial method. So apart from n and d, we'll introduce some new definitions, where delta is the goal difference for a current state, and BD and delta is the number of ways to achieve a certain state, with n the total goals and delta the score difference. Also, we have SDN, which is the answer we are investigating on, which is the number of ways to achieve with n is being the total goals. So below is an example for the definitions. So we can see that each entry is also the sum of 2 of the entries above it, just like a Pascal's triangle. So we can define it as a pseudo-Pascal's triangle, and we can try to write each entry in terms of binomial coefficients to look for some patterns. So before writing in terms of binomial coefficients, here is a simple illustration. So now, when we need to formulate the construction for the binomial coefficients, we have these 5 formulas, where the first formula is for the base case, and other 4 formulas are about some special cases and the transition cases. So here is an example of the tree of d is equal to 2 up to the 5th row. So we can see every term can be expressed in binomial coefficients. So we have another larger example of BD and delta, where we found that by hand calculation, we have B3, 21, 3 equal to this series of binomial coefficients sum. So by further calculation and exhaustion by hand, we can deduce a formula of calculating the general value of BD and delta, which is shown here. So it's sufficient to prove this star can satisfy these 5 formulas. So finally, by simple summation of every BD and delta for every different value of delta, we can obtain a formula for SDN as shown here, considering the parities of n and d. So now we move on to the third part, which is the matrices method. We'll define the counting vector being VDN, which is representing every BD and delta. So it represents all states, where we're calling that mass difference is d, and n is the number of total goals. So now we have the initial counting vector, VD0. The vector is shown, the form of the vector is shown here, because only possible B0, 0 delta, the only delta should be 0, so only the middle have 1. So for a better example, we have the first counting vector of V3n shown here. So now we can determine every element of the vector VDN from the translation formula similar to the pseudo-Pascal triangle. So we can see that every element is determined from the previous vector VDN minus 1. So now we can try to find a transition matrix, MD, such that VDN is equal to MD times VDN minus 1, where MD is shown here. So applying this formula recursively, we can have VDN equal to MD to the nth power times VD0. So in the original problem, we can recall again that d is equal to 2 and n is equal to 12. So V212, the vector should be in this form, so we can still calculate the answer, which is 972. So now we have to find MD to the nth power for large n effectively. So we are going to diagonalize MD. So the form of a tridiagonal Topliss matrix is the following for our MD matrix, where A minus 1, A0, and A1 are real numbers. So from a research done with banded Topliss matrix, we have the tridiagonal Topliss matrix where we can define the eigenvalue and the eigenvector for those matrices as shown here. So when substituting the value of A0, A minus 1, and A1 as shown here, we can write MD equals to PD times DD times the inverse of PD, where we can determine the elements of PD and DD from simply by obtaining from the results from that research as shown here. So for example, when D is equal to 2, we have P2 and D2 from simple direct substitution. So we also found that the inverse of PD is equal to 1 over D plus 1 times PD. So we can rewrite the form of MD to the nth power as shown here. So by substituting the value of MD into the first formula, which is VDN, so we can have a simple calculation of every element of VDN, which is the formula shown here. So we have SDN is summing up every element in VDN. So by simple summation, we have a formula for SDN for which we can see there are two summation symbols. However, this is quite complicated. So we have developed two lemmas shown here, so we can further simplify this formula for SDN. So after simplification, the form of SDN only have one summation symbols. So again, by considering the terms eliminated when D and N are the same or different parities, we will have two separate formulas for SDN. So now we have solved the problem with the combinatorial method. However, we have to extend the problem by considering into probabilities, where let P be the probability of the first team to score a goal, and let V prime dn be the vector of probabilities. So now we can also define S prime dn similarly. So the calculation of V prime dn and S prime dn is very similar to the previous session. So the calculations are not shown here. So we have, after our calculation, we have V prime dn and S prime dn formula as shown here. So we can finally move to the results of these two parts. Recall that we have used combinatorial method and matrices method to obtain the same value, which is SDN. So we can equate both sides to obtain another equation consisting with binomial coefficients and trigonometric terms. So this is the result of these two formulas. So we can see the left side is the binomial coefficients and the right side is the trigonometric terms. Observe that these angles of the trigonometric terms are special angles if D is equal to 1, 2, 3, or 4, and 5. They can give rational numbers or even simple surd forms. However, when D is equal to 6, which is the first positive integer of D such that these angles are not special, they cannot be expressed in terms of simple surd forms or rational numbers. So we can see that this formula can non-trivially express the sum of binomial coefficients in terms of a series of trigonometric coefficients. For example, when D is equal to 1, we can have the right-hand side of the trigonometric term being simplified to a simple power of 2. And when D is equal to 2, we will have the trigonometric terms equal to a power of 3 times 2, which is a simple form. And when D is equal to 3, we will have those special angles for the trigonometric term giving surd forms. Finally, when we also give a final example, when D is equal to 6, we have this form here where the angles cannot be further reduced. So we can finally deduce that these formulas are determined so non-trivially. So in conclusion, we have done some the solution to the original problem we were investigating on the closed mesh in session 1, and we have discovered the properties of pseudo-Pascal's triangle and developed the formula of SDN in session 2. And in session 3, we have formulated the value of VDN and SDN using the theorems regarding tridiagonal Topliss matrices. So in the final session, in session 4, we've combined two methods to obtain a non-trivial formula for trigonometric terms and binomial coefficients. This is the end of our presentation. Thank you.